Okay, so in this video we're going to be looking at work and energy. So the equation that we use for that is going to be U12. I'm writing the full equation, so you have U12 prime, which is equal to delta T plus delta Vg plus delta Ve, if I'm not mistaken. So delta T, this is your kinetic energy. Delta Vg, this is your gravitational potential energy. And then this is your elastic potential energy. So kind of like a spring or a rubber band or whatever. So that will be captured in this term over here. And then over here we have the work done by any force onto the system, right? So if no work is done, then U12 prime will be equal to 0. However, if work is done, then it won't be equal to 0. Okay, so typically for questions like this, you'll be given two states, right? When you need to actually implement this equation, you'll be given two states, and then you would probably be told that it's frictionless, right? Because if you had to account for friction, then work would be done. And let's say that you have like a curved surface, kind of like that, you can see that it would be very difficult to account for friction. So let's say that we had a ball starting from the top and it rolls down to the bottom over here. So the work done by friction would be all the way along this distance over here. So if they asked you to solve for that, you would need to find this arc length, which is possible to solve for. Like let's say this was 90 degrees, then the arc length will be theta multiplied by r, right? But if they don't give you that information, then you can't solve the problem using work energy, right? So yeah, typically they'll tell you it's frictionless, but yeah, don't bank on that. There might be cases where you have to account for friction. And then remember, work done is force times distance, right? But then the distance is the distance the object moves in the direction of the force, right? So let's say we have a block. So going back to F as K, you have a block, a force is being applied, but the block only moves upwards, right? So it only displaces upwards, but the force is still acting that way. This force then doesn't do any work, right? Because the distance that the block moved is not in the direction of the force. Okay, cool. Hope that makes sense. And then going back to this equation, if you look at this equation, this basically accounts for not all forms of energy in the system, because there's still things like thermal, sound, and all of that this equation doesn't account for. So if they tell you energy is lost due to sound, or there's an explosion, if there's an explosion or whatever, then this equation can't account for the thermal energy lost, and the sound energy that's lost. So yeah, this just accounts for the dynamic energy, if you could call it that, right? And let's say we have a case where U12 prime is 0. Then at state 1, we're going to have T1 and plus Vg1 plus Ve1 equal to T2 plus Vg2 plus Ve2, right? So, for example, if at state 2 I gain kinetic energy, so an example of that would be like a ball starting at the top of a hill and then it rolls down and it gains kinetic energy. So this is state 2, this is state 1, right? So it gains kinetic energy, right? Then if it's gaining kinetic energy, in order for these two terms, well, this side of the equation to equal that side, we have to lose something. So in this example over here, there's no spring, so there's no elastic potential energy stored, right? The thing that has to go down then is my gravitational potential energy. So you can see that as the ball goes down, it increases its kinetic energy, but then because its height is decreasing, right, it's losing gravitational potential energy. So this equation just basically tells you how energy is transferred into different forms, right? But now if you had a force applied, you have an external factor increasing the amount of kinetic energy that you have at a faster rate. So if you had a force applied over here, right, and it's constantly acting throughout, then your kinetic energy would increase much more than the gravitational potential energy decreases. So now all of a sudden these two parts of the equation are not equal to each other, right? Because there's some external factor speeding the process up or adding more energy to the system. That's accounted for by this U12, which is the work done by any external forces. So yeah, remember U12 is only work done by external forces. It doesn't account for thermal energy or whatever. So yeah. Also, like if you had friction, for example, then you'd increase your thingy. You'd increase your kinetic energy. So let's draw that case in. So let's say we had friction slowing this thing down, right? So I'm going to indicate that with a small f. So friction is slowing this thing down, so it's not going to go as fast, and your gravitational potential energy is still going to decrease at the same rates that it was before, right? So now if you were to take the difference between these two sides, your gravitational potential energy is decreasing a lot more than this is increasing. So you're going to have a net negative, right, if you take the difference. So all that is saying is that the friction is removing energy from the system. So then U12 prime would be negative in that case. So in the case of friction, U12 prime would be less than 0, so negative. Also, friction is working in the negative direction in this case, so hence it's gonna be negative. But essentially, if U12 is greater than 0, then energy is added. If U12 is less than 0, energy is removed from the system, and then if U12 is equal to 0, then energy is conserved. Okay, cool. I hope that makes sense. Okay, let's do an example with that. So we're given this example where 3 small steel balls each have a mass of 2.75 kilograms. They're connected by the hinged links of negligible mass and equal length, and then we're told that they're released from rest in the positions shown, and then they slide down a quarter circle, cool when the upper sphere reaches the bottom position. The spheres have a horizontal velocity of 1.56 meters per second, and then we're asked to calculate the energy loss due to friction and the total impulse on the system. Cool. So in this case over here, we're given two states, right? So we have state 1, where the spheres are oriented like that, and then state 2, where everything is going to be horizontal. Well, yeah, basically at the same level, right? And then we're asked to calculate the energy loss due to friction, right? Cool. So we know that U12 in this case isn't going to be equal to 0 because there's some work done by that friction. There's some energy that's removed by that friction. But we can still calculate it as long as we have all the other terms in our equation. So remember, U12, I'm going to say prime, and then, yeah, we'll scratch out that elastic potential energy term. So you have delta T plus delta VG plus delta VE. That's going to be equal to 0, right? And then you're going to have T2 minus T1 plus VG2 minus VG1, right? As long as we have all the necessary information to fill in these terms, then we can solve the problem, right? So we're told that it starts off at rest, and then, right, so it's released from rest, and then it moves to this position over here in state 2. Cool. So we're going to start off with T1, right? T1 is just a half mv squared, right? And then we can either do it for each and every particle, so meaning we can take the sum of 1/2, just take that outside, mi vi squared, right? Or we could say, going back to FSK, this is what we did, right? We always looked at the system as a whole. So instead of looking at each and every single particle, we clumped everything into a point particle, and then took the total mass and then the velocity of the center of gravity, right? So these are our two options, right? So for state 1, it's easier to just use a half m total times Vg squared, right? Because Vg is 0, right? So T1 is equal to that Vg squared, which is just going to be equal to 0 because Vg is equal to 0. Cool. Then for T2, we're told that everything is moving at the same velocity, right? Because everything's linked together. So everything has to move at the same velocity, which then means that the center of mass is also going to be moving at that same velocity, right? So everything is moving at 1.56 meters per second. So then T2 will be equal to 1/2 m total times Vg squared, which will equal 1/2 3 times, I think it's 2.75, right, times 1.56 squared. Okay, then we can do Vg1. Okay, so same as T, your kinetic energy. With Vg, you can either do it for each and every particle, or you could do it for the center of mass, right? So we're going to have Vg1 is equal to either the sum of MI G HI, yes, or VG1 will be equal to M total times G times H of the center of mass of G, right? So because we don't know the position of the center of mass, you can go and calculate it if you wanted to, but it's honestly not necessary. It's a lot easier to just do the heights for each and every sphere, right? And in doing so, we're going to first define a datum or a reference line, right? So I'm going to say I'm taking all my measurements from here, from this line over here, right? I'll call that x prime, for example. And then everything above this line is positive, everything below this line is negative. Okay, so this first position over here, that's going to be 0.36 meters, and then you have to do some weird trick to try and find this over here. What would that even be? I'm not gonna lie, don't really, wait. No, this angle is equal to that one, and then yeah, no, hey, not gonna lie, I'm not seeing it, shame. Wait, then that right angle triangle, but I don't know any distance there. Perhaps, okay, but yeah, there's some weird trick that you could probably do to find out this height. So you'd need this distance here. Just gonna call that y for now. Okay, so for VG1, we're gonna have the first mass, which I'm gonna treat as this one over here, the top one. So that's gonna be 2.75 times 9.81 times its height, which is 0.36. Then we're going to add to it the next one, which is going to be 2.75 again, because they have the same mass, times 9.81 times its distance, which we're going to call y in this case, then plus 0, right? So this one over here is at our reference point. So we're going to say that has a height of 0. Okay, and then for VG2, at state 2, everything is in line with our reference line, right? So we're going to say VG2 is equal to 0 because H is equal to 0, right? Now we have all our different components, right? And we can substitute it into this equation and solve for the amount of energy that would have been lost due to friction. Okay, and then the second part of the question says that we should find the impulse, Ix. So the impulse is basically the rate of change of momentum. So Ix is just, well, if you want to be technical about it, it's then to go from T1 to T2 of G, is it G dt, which is just equal to, in the x direction, which is just equal to delta Gx. So at state 1, we start with Vx equal to 0, so then Gx will be 0, right? Because remember, Gx will just be the sum of mi vi in the x direction, right? But everything is stationary, so this will be 0. Okay, and then for state 2, Vx for the whole system will be equal to 1.56 meters per second, right? So then Gx for state 2 will be then equal to, it will be equal to the sum of mi vi x, but it's also equal to the total mass times Vg, right? And since everything is moving with the same velocity, Vg will be equal to 1.56. So this will be equal to 3 times 2.75, I think it is, times 1.56. Okay, hope that makes sense.